In this course, we will discuss about the basic principle of NMR and MRI. NMR can literally be broken down into three parts. We have nuclei, magnetic, and resonance. And then, of course, there is imaging, which we are not going to talk about today. First, we need to know which nuclei have NMR phenomenon. Not all nuclei of elements can undergo NMR. And then the magnetic field environment corresponds to our NMR device, which is the magnetic provides the magnetic field environment. And we also have to figure out how the nuclei acts in the magnetic field. The third is the resonance. We need to know under what conditions atomic nuclear energy resonates in the magnetic field. Last part is imaging. Magnetic resonance imaging, MRI, asks for a gradient magnetic field. The gradient of the MRI is the main function of space positioning. With the spatial orientation and coding, we can get the two-dimensional or three-dimensional MRI. We are not going to details today, and let's talk about it later. We are going to explain these three parts today. The first is the nuclei. First, we let's take a look at this diagram. It is well known that the molecules are made up of the atoms, and the atoms are made up of the nuclei and the extrinsic electrons. The NMR is mostly about the nuclei, so we need to understand that. The nuclei is composed of protons and neutrons, and the spin quantum number I of both protons and the neutrons is a half. According to the value of the spin quantum number, we can divide nuclei into three types. The first is the nuclei with spin quantum number I equals to 0, which have an even number of the neutrons and protons, such as the carbon 12, oxygen 16. The second type of nuclei is characterized by a half integer spin quantum number and an odd number of the protons and the neutrons. For example, the thorium 19, the carbon 13, and hydrogen 1. The third is nuclei whose spin quantum number is an integer. These nuclei have an odd number of protons and neutrons, like carbon 14 and hydrogen 2. So the second and the third type of nuclei, where the spin quantum number is not 0, they have the NMR phenomenon. And the nuclei with spin quantum number equals to 0 has no NMR phenomenon. Most of the nuclei in our periodic table are capable of NMR. The nuclei that we use the most often is hydrogen. Most medical magnetic resonance imaging and relaxation analysis are based on the hydrogen nuclei. Also, our experiments in this course also based on the hydrogen nuclei, those samples. Well, the second part is the magnet, which is the magnetic field. It is one of the most important components of NMR. Magnets, which provide the magnetic environment, it can be classified into three categories. The first type is the permanent magnets. Permanent magnets are made of the magnetic materials. The equipment involved in this course is a permanent magnetic system. Well, this part, this part here is the magnet. Well, the second type is the normal conductive electromagnet. It is made of the wire wound and is energized to produce a magnetic field. The magnetic field composed of no normal conductive magnets generally has a low magnetic field intensity, such as zero point 0.2 Tesla, zero point 0.3 Tesla. The third type is the superconductive magnets. The superconductive magnet is also an electromagnet, but it is one with the superconductive material. And then the superconductive material is placed in an ultra low temperature environment so that the coil is in a superconductive state. And after the electricity is energized, a strong magnetic field will be generated. So, such magnetic field strength is very high, generally more than 1.5 Tesla. Now let's look at this equipment. This is our NUMAC EDU series of MRI technology test instrument. This is the magnet. This is the magnet. And the magnetic field is zero point 0.5 Tesla. And this is a simple diagram of the inside of the magnetic field. And these two cylinders are the magnetic poles, and there's a gap between the two poles, which is where you put the probe, and the test sample is placed between the poles. Magnetic probes, um, the magnetic poles creates an equilibrium and stable magnetic field environment. The outer the outer part is the magnetic yoke. The magnetic yoke is mainly used to restrain the magnetic field and keep the magnetic field balanced and stable. Well, the yoke prevents the magnetic field from leaking out and interfering with external instruments, and also protects the magnetic field from the foreign magnets. The yolk usually use soft tissue with high extraction rate, such as the silicone dry sheet. This is the magnetic field of the permanent magnet. The magnetic resonance can also be divided into low field, middle field, and high field according to the magnetic field strength. The low field is generally below 1 Tesla. The middle field is between 1 Tesla to 1.5 Tesla, and the high field is above 1.5 Tesla. Actually, there is no special unified method of differentiation, mainly to help you understand it. No matter the type of the magnet and the intensity of the magnetic field, the function of magnets provide is to provide a balanced and a stable magnetic field environment. This is very important. The magnetic field uniformity is a very important technical indicator for relaxation analysis, the magnetic resonance imaging, or the spectroscopy. We talked about the nuclei and the magnetic field. The NMR phenomenon also requires the nuclei to be associated with the magnetic field. Let's take a look at what happens to the nuclei when it's in a magnetic field and when it's not. Let's take the case of the hydrogen nuclei, which has only one proton. It is positively charged and produced a spin magnetic momentum. We can think of the hydrogen nuclei as a little magnetic needle. In fact, Each hydrogen nuclei can be taken as a little magnetic needle. There are a lot of hydrogen nuclei in the sample. When there is no magnetic field in the sample containing hydrogen, the arrangement the arrangement of hydrogen in the sample is chaotic and does not show magnetism in general. When we place the sample in a magnetic field of B0, the hydrogen the hydrogen nucleus will be oriented after the magnetization process. After reaching equilibrium from a macroscopic point of view, the longitudinal magnetization vector will be generated. We use the M0 to represent the magnetization vector. Now, when you get to this state, the whole system is in equilibrium. The longitudinal magnetization vector M0 is constant. And when we are in equilibrium, let's look at the hydrogen nuclei. In a magnetic field, the hydrogen nuclei is always moving. There are two kinds of motion in the hydrogen nuclei. The first is spin, and the spin always exists. The second is that in a magnetic field, hydrogen nuclei will be affected by magnetic force and move in a circle around the magnetic field. This is known in NMR as Larmor precession. The Larmor precession has an inherent frequency called the Larmor frequency. This is the formula for frequency. Well, the Larmor frequency, which is called omega 0, is equals to gamma times B0. Gamma is called the gyromagnetic ratio. The gyromagnetic ratio has different value for different nuclei, but for the certain nuclei, it's a fixed value. For example, the gyromagnetic ratio of hydrogen nuclei is 42.58 megahertz per Tesla. It is equal to the Larmor frequency of hydrogen nuclei, which is 42.58 megahertz under the field intensity of 1 Tesla. The magnet resonance device, the EDU-MR we mentioned earlier for this course, has a field strength of a half Tesla. According to this Larmor formula, the resonance frequency of this device is about 21 megahertz. As some of you may know, NMR is called in two different ways. You can call it a half Tesla NMR machine. A half Tesla refers to the strength of the magnetic field. Another way to call it is an NMR machine called 21 megahertz, which is actually the resonance frequency of it. Of course, this is the reference frequency of hydrogen nuclei. So the transformation relationship between megahertz and Tesla is completed by Larmor formula. For example, 300 megahertz nuclear magnetism corresponds to a magnetic field strength of 7 Tesla, and 60 megahertz nuclear magnetism corresponds to a magnetic field strength of about 1.4 Tesla. The third part is resonance. The essence of resonance is the transfer of energy. Take the tuning fork, for example. Look at the two tuning forks in the picture. If they have the same frequency, the one of one of them vibrates, the other one close to it vibrates as well. That's resonance. It's a tuning fork that transfers energy through resonance to the other tuning fork. If the frequencies of the two tuning forks are not equal, there will be no resonance and no energy transfer. The MRI works the same way. Nuclei in a magnetic field needs to meet certain conditions to produce resonance. We can apply radio frequency pulses, and when the frequency of the radio frequency pulses is consistent with the Larmor frequency of the nucleus in the magnetic field, the resonance occurs. This is our equipment. This is a magnetic field. This is the magnetic field, and we have probe in it. The probe is here. The sample is put into a magnetic field, and when the sample with hydrogen is put into a magnetic field, its natural frequency is fixed. Because the hydrogen nuclei are certain, so is the spin magnetic ratio, and the strength of the magnetic field is also fixed. On the left are the electronic devices that they can emit RF pulses of a certain frequency on request. The frequency of the RF pulse can be adjusted, and the NMR phenomenon occurs when the RF pulse frequency is equal to the Larmor frequency. The MRI signal can be detected from the device. That's how the MRI works. So we've broken down NMR into three parts, and I'm going to summarize this. The first thing you have to do is to have a nuclei that has NMR phenomenon where the spin quantum number I is not equal to 0. Secondly, it is necessary to provide a stable and homogeneous magnetic field. The nucleus will have a certain frequency in such magnetic field. For example, the gyromagnetic ratio of the hydrogen nucleus is 42.58 MHz, and the natural frequency of hydrogen nucleus can be calculated by this formula. The condition for resonance is that the frequency of the RF pulse is equal to the Larmor frequency. Then the nuclear magnetic resonance phenomenon can occur and the signal of nuclear magnetic resonance can be detected. Let's talk a little bit about how NMR happens. The sample placed in a magnetic field generates a constant longitudinal magnetization vector represented by mz, followed by the application of a ratio frequency pulse, which occurs when the frequency of the radio frequency pulse is equal to the Larmor frequency. From the microscopy point of view, it is the nuclei of different energy levels that absorb RF energy and make the transition from the lower energy level to the higher energy level. From the macroscopy point of view, it is the longitudinal magnetization vector deflection. The angle of deflection is related to the energy of the applied RF pulse. A 90-degree deflection is a 90-degree pulse. A 180-degree deflection is a 180-degree pulse. The angle of deflection is arbitrary and can be calculated from the parameters of the RF pulse. To better understand it, we can think of the magnetization vector as a spring. Spring is the spring is compressed at an angle by an external force. When the external force is removed, the spring will return to its original state. The deflection of the longitudinal magnetization vector is similar to that of the spring. When we turn off the RF pulse, the deflection magnetization vector returns to its original state. This process of recovery is called relaxation. The relaxation process can be decomposed into two parts. The first part is the horizontal decay from the maximum decay to zero. The second part is the vertical recovery from zero to the original state. The longitudinal recovery process is called the longitudinal relaxation process, and the speed of the recovery is described by the longitudinal relaxation time T1. The lateral decay process is called the transverse relaxation, and the speed of the decay is described by the relaxation time T2. In fact, the whole process is a spiraling process. In our device, the sample is placed inside the probe. The spiral rise of the magnetization vector will cut the coil and cause a change in the magnetic flux in the coil. And the change in the magnetic flux produces an induced electromotive force or induced current, which the probe detects, and that is the NMR signal. This signal is the attenuation of the attenuation of the oscillation, and the frequency of the oscillation is the Larmor frequency. So this signal is also called FID signal, free induction decay. At this point, the basic principles of the nuclear magnetic resonance are introduced, and later our experiments will further verify and explain the names and the phenomenon in the process. Thank you.